Chapter 5 Heat. We come across the term heat quite frequently in our daily lives. Our life is greatly influenced by the term heat directly or indirectly. In this chapter, we are going to explore some more concepts related to heat that we experience almost daily. But before we learn the different concepts of heat, let us first try to understand what exactly is heat and temperature and the basic difference between them. Heat. Heat is a form of energy which produces in us the sensation of warmth. It is the transfer of thermal energy from one body to another in which no mechanical work is done. The term hot and cold are often used by us. For example, if we touch a burning coal, we feel it hot, and if we touch ice, we feel it cold. Temperature. Temperature is the degree of hotness or coolness of a given body. The sensation of touch helps us to determine the degree of hotness or coolness of a given body. We need accurate and exact measurement of heat. Hence, we take the help of an instrument called thermometer. So in short, heat is the energy, whereas temperature is the amount of that energy that we measure using a thermometer. In our previous standards, we have learnt about the different ways of heat transfer. They are conduction, convection, and radiation. What is latent heat of fusion? The quantity of heat utilized by a substance to change from solid state to liquid state without a rise in temperature is called latent heat of fusion. Let us understand it by a short experiment. Take about 200 grams of small ice cubes, put them in beaker, place the beaker on a burner, then put thermometer in the beaker. Start noting the temperature at every 1 minute. It will be observed that ice starts to melt when heat is supplied to the beaker which contains ice cubes. The thermometer shows 0 degrees temperature. Supplied heat does not get recorded. But where does this hidden heat energy go? This hidden heat energy is utilized for weakening the interparticle forces or the bonds between the atoms during the change of state and is called latent heat. When the whole ice is melted, its temperature starts increasing, and when we further heat, the water starts boiling. Now it changes its state to gaseous form. The temperature now remains the same, that is at 100 degrees Celsius, till all the water gets converted into steam. And after this stage, the temperature starts to rise again. The amount of heat energy absorbed at constant temperature by unit mass of a liquid to convert into gaseous phase is called the specific latent heat of vaporization. If we plot the graph of temperature versus time, with temperature on y-axis and time on x-axis, it is observed from the graph that 1. BC is the region where ice starts melting, where the temperature is constant 0 degrees. Second, CD is the region where ice is completely converted to water. The temperature starts rising. Third, DE is the region where water starts boiling. Temperature is constant 100 degrees. Fourth, EF is the region where the water is converted into steam. Temperature rises above 100 degrees. Regelation. Regelation is the process by which a substance melts under a pressure and refreezes after the pressure is released. Experiment. Take a slab of ice on a stand as shown in figure. Take a metal wire with its end tied with equal weights. Put the wire on the slab as shown in the figure. It is observed that the wire comes its way slowly through the block of ice due to the pressure on its ends rather than breaking the ice. As the wire releases the pressure from the top, the ice block will refreeze and the wire will finally be taken out of the bottom of the ice slabs. This phenomenon, in which the ice converts to liquid due to applied pressure and then reconverts to ice once the pressure is removed, is called regelation. Most of the liquids expand on heating and contract on cooling over a moderate range of temperature, but water shows a marked exceptional behavior. When water is heated from 0 degrees Celsius, initially it contracts in volume up to 4 degrees centigrade instead of expansion. As the temperature goes beyond 4 degrees, the volume keeps on increasing, that is, it expands. This distinct behavior of water from 0 degrees to 4 degrees is said to be anomalous behavior of water. Let's study this phenomenon using Hope's apparatus. Hope's experiment. The anomalous behavior of water can be studied with Hope's apparatus. A flat bowl is attached to a cylindrical container as shown in figure. Thermometers are attached above and below the flat bowl on the cylindrical container. Water is filled in the cylindrical container and a mixture of ice and salt, also known as freezing mixture, is put in the flat bowl. During the study of anomalous behavior of water using Hope's apparatus, temperature T1 and T2 are recorded after every 30 seconds. The temperatures are plotted on the y-axis and the time in minutes on x-axis. The graph is shown in figure. The graph shows that initially both the temperatures T1 and T2 are identical. However, as time passes, temperature T1 of water in the lower part of the cylinder decreases fast, while temperature T2 of water in the upper part of the cylinder decreases comparatively slowly. However, once the temperature T1 of the lower part reaches 4 degrees Celsius, it remains almost stable at that temperature. T2 decreases slowly to 4 degrees Celsius. Thereafter, since T2 starts changing rapidly, it records 0 degrees Celsius first, and after that, the lower thermometer T1 records 0 degrees Celsius temperature. The point of intersection of the two curves shows the temperature of maximum density. How can we explain these observations? Initially, the temperature of the water in the middle of the cylinder lowers due to freezing mixture in the outer bowl. Since the temperature of the water there decreases, its volume decreases and its density increases. The water with higher density moves downwards. Therefore, the lower thermometer T1 shows rapid fall in temperature, and this continues till the temperature of water becomes equal to 4 degrees Celsius. When the temperature of water starts decreasing below 4 degrees Celsius, its volume increases and the density decreases. It therefore moves in the upward direction. The temperature of water in upper part, that is T2, therefore decreases rapidly to 0 degrees Celsius. The temperature of water in the lower part, that is T1, however, remains at 4 degrees Celsius for some time and then decreases slowly to 0 degrees Celsius. The anomalous behavior of water plays an important role in the survival of aquatic plants and animals in cold regions. In cold countries, the temperature of the atmosphere may fall to 0 degree in winter. The water at the surface of the pond and the lake begins to contract as a result. The volume decreases and the density of water on the surface increases, which then begins to sink to the bottom. This process continues till the temperature of all the water in the lake falls to 4 degrees Celsius. That is, it begins to expand instead of contracting. Consequently, its density decreases so that it remains on the surface. The temperature of the water at the surface goes on decreasing to 0 degrees Celsius, and finally the water gets converted into ice. Water below the ice continues to remain at 4 degrees. Thus, at 4 degrees Celsius, fishes, aquatic animals and plants are survived. In winters, sometimes the pipelines carrying the water burst. When the temperature of the atmosphere falls below 4 degrees Celsius, water in the pipes begins to expand. At 0 degrees, it turns into ice. That creates pressure in the pipes and the pipelines burst. Crumbling of rock into pieces. Water enters into the narrow cracks of rock. When the temperatures of the surroundings falls below 4 degrees, the water begins to expand. As there is no place in the narrow crack for expansion of water, thus tremendous pressure is exerted on the rock and it breaks into pieces. Dew point and humidity. 71% of Earth's surface is covered with water, and evaporation of water takes place continuously. Hence, the atmosphere always contains some quantity of water vapor. Illustrations. Number 1. When we enter in a warm room after being outside on a cold early morning, spectacles steam up. Because the temperature of the outside air is below a particular temperature of the air in the room, also called the dew point, therefore the water vapor condenses upon the glass. Number 2. A cold drink bottle taken out of refrigerator. We observe that the water condenses on the bottle. The amount of water vapor present in the atmosphere determines the nature of the weather. A given volume of air can contain maximum amount of water vapor at particular temperature and is said to be the saturated water vapor with that temperature. The quantity of water vapor required to saturate the air depends on the temperature. If air contains a quantity of water vapor less than the maximum quantity of the water vapor it can hold, the air is said to be unsaturated with the water vapor. Dew point. When the sample of air is cooled sufficiently, the water vapor present in it gets saturated. Some water condenses into water droplets. The temperature at which the air becomes saturated with water vapor is called the dew point. Humidity. The dampness or moisture in air due to water vapor content is called humidity. Absolute humidity. The percent of water vapor present in the air, if measured in terms of quantity, is called absolute humidity. The mass of water vapor per unit volume of air is called absolute humidity. Dry air. If the quantity of water vapor present in the air is very small compared to the quantity required to saturate air, we feel that the air is dry. Moist air. If the quantity of water vapor present in the air is little less than the quantity required to saturate the air, we feel that the air is moist. Relative humidity. The degree of moistness of the air is determined by a quantity called relative humidity. It is defined as the ratio of the mass of the water vapor actually present in the given volume of air to the mass of the water vapor required to saturate the same volume of the air at the same temperature. At dew point, relative humidity is 100%. If relative humidity exceeds 60%, we feel that air is moist. If it is below 60%, we feel that the air is dry. Example: on a clear day, white trails may be seen behind high-flying aircraft. The water vapor from engine condensed to form a cloud. If the surrounding air is moist, having more relative humidity, trails are long and takes long time to disperse. If the relative humidity is low, the trails are short or may not form at all. Units of heat. Heat is a form of energy like light or sound. Its CGS unit is calorie. Its MKS unit is kilocalorie. Its SI unit is joule, denoted by J. Calorie is the quantity of heat required to raise the temperature of 1 gram of water through 1 degree Celsius from 14.5 to 15.5 degrees Celsius. A kilocalorie is the quantity of heat required to raise the temperature of 1 kilogram of water through 1 degree from 14.5 to 15.5 degrees Celsius. Specific heat capacity. Specific heat capacity is defined as the quantity of heat energy required to raise the temperature of unit mass of the substance through 1 degree Celsius. It is usually denoted with the letter C. Its unit in CGS is calorie per gram degree Celsius. Its unit in MKS is kilocalorie per kilogram Celsius. Experiment of specific heat capacity with 3 solid spheres. For this experiment, take 3 solid spheres made with iron, copper and lead, each having the same mass. Heat them together in boiling water. After some time, remove them from boiling water and keep them on thick slab of paraffin wax immediately. The paraffin wax will melt, but we will notice that different spheres penetrate to different depths into the wax, and quantity of wax melted is different for different spheres. The sphere that gives out more heat will melt more wax and will penetrate deeper into the wax. Specific heat of iron is more than copper and lead. Hence, iron sphere will absorb more heat, copper will absorb less, and lead even lesser from boiling water. Iron sphere will give more heat to the slab, lead sphere will give least heat to the slab. This observation shows that the above 3 spheres have absorbed different quantity of heat from boiling water. This indicates that the sphere must possess some property which changes from material to material. This property is called specific heat capacity of a substance. Heat exchange. When a hot body is kept in contact with a cold body, it has been observed that the temperature of the hot body goes on decreasing and the temperature of the cold body goes on increasing until both the bodies attain the same temperature after some time. In this process, the hot body loses heat and the cold body gains heat. If the system of the two bodies is kept isolated from surroundings so that no heat enters or leaves the system, then heat lost by the hot body equals heat gained by the cold body. This is called the principle of heat exchange. This principle is useful in determining the specific heat of any other substance. Measurement of specific heat, mixing method and calorimeter. The specific heat of a metal can be determined by the method of mixtures. The apparatus consists of a calorimeter surrounded by the wool to prevent loss of heat by conduction and is kept in a wooden box. When a hot solid is introduced into the water in a calorimeter, heat is transferred from hot solid to the water and the calorimeter. Such transfer of heat continues till the solid, water and calorimeter attain the same temperature. Note that the calorimeter is surrounded by non-conducting material like wool, thermocol and cotton to avoid the heat transfer due to radiation to surrounding and vice versa. Therefore, heat lost by the solid, or Q, is equal to mass of solid multiplied by specific heat capacity of the solid multiplied by the fall in temperature. Heat gained by water, or Q1, is equal to mass of water multiplied by its specific heat capacity multiplied by the rise in temperature. Heat gained by the calorimeter, or Q2, is equal to mass of calorimeter multiplied by specific heat capacity of its material multiplied by rise in temperature. Therefore, heat lost by solid is equal to heat gained by calorimeter plus heat gained by water. Therefore, Q is equal to Q1 plus Q2. Using this formula, one can determine specific heat capacity of the metal.